Hello, everybody, and welcome back to, I think, what will be the final video in the PK series because the next exam won't really be as math heavy. I don't think we'll really need a video for it, but we definitely did a video for this. I started going over it today, actually. I thought this would be an easier video to make. And as I go through the renal and hepatic mathematics, I realized that I did not know what I was doing. So I spent a lot of the afternoon figuring it out. I think what made this extra complicated was the fact that the units were very inconsistent. Equations were randomly in calculus forms, and they didn't need to be. Constants would appear out of nowhere. So it took a lot of research on my part to track down kind of what was trying to be communicated in these lectures. But I think I've done it in such a way that I can really simplify some of these units. I'll work through a couple practice problems, but I really just want to show kind of how these units relate to each other, how we can expect to see them in a problem. But yeah, with that out of the way, let's get started. So we'll start with renal elimination. This is probably going to be the bulk of our exam math-wise, and it starts off relatively simple with things we've seen before. Clearance T, also sometimes denoted as clearance S. I've tried to make it clearance T for the purposes of this lecture, but Dr. Desai has used them interchangeably. Is our systemic clearance or our total clearance we're used to, right? We have our elimination rate constant, our K10, which indicates all elimination, and then our volume of distribution. We've had this exam since exam one. We've used it sparingly just to solve a couple of random problems, but it's really kind of the focal point of this exam. Um, so next up, you can see we have some very similar equations. Really the two we need to be more familiar with, or I won't even say two, I'll say one, is this renal elimination constant. We will have a little bit of things to do with this hepatic elimination clearance, but it really does come down to renal. Um, so this KE is, I think it stands for K excretion. I'm not really sure. But the way I think of this is just when things are eliminated, right? They're either metabolized or excreted. Things aren't excreted through the liver. There's no exit hole. The kidney, though, obviously you can urinate something out. So that's why I think of this one as excretion. So whenever we see clearance renal, we can pair it up with this KE. Likewise, clearance hepatic is, I think KM stands for clearance or rate metabolism, and then clearance B, I believe, is biliary, which we never really use this bottom one. I don't even know why I had it on here, to be honest. I guess it could be useful for some problems, but really our bread and butter are going to be our renal and our hepatic. And usually we're solving for renal and getting hepatic kind of secondarily because it's a lot harder to measure hepatic elimination just for the sense that it's so easy to collect a drug in urine versus going into the body intrusively and collecting something hepatically is harder. So as you can probably guess, all these constants are related to each other, and our total clearance is just equivalent to the sum of our renal clearance or hepatic clearance, any other type of clearance we may have. Things may get excreted through sweat, may get excreted through breast milk, just various pathways, saliva. But this all sums up to our total clearance and these subsets of equations with these subsets of KEs or KMs in the case of liver. So what are some constants we need to know? So one constant is known as the clearance renal of inulin. This is similar to creatinine clearance. It's a measure of GFR. You may remember back from renal that serum or creatinine in the proximal tubule is actually secreted. We can't always get an accurate measurement of GFR. Inulin is a protein, or I think it is at least, I don't know, it ends in IN, but the point is it's not secreted. That's really what matters. So the average GFR in a healthy person is 120. However, I will note that he does have it on his exam sheet as 125 milliliters per minute. I would probably stick with the 125. I will be doing that for purposes of calculations of this video. However, this 120 is also pulled directly from his slides. So I wanted to put both on here just to make you aware. This is an equation that's not on the exam sheet, but I would really emphasize and encourage you to remember it. This is your total clearance times your fraction eliminated equals your clearance renal. Right, this is essentially just a fractional multiplication. Similarly, you could write your clearance total is times your fraction hepatic. It's equivalent to your clearance hepatic. right? And it's essentially just showing this fraction of total will be your individual. Pretty simple concept at first glance. I meant to erase that. But it helps with so many problems, and I'll show you how many times I end up using it. I really do think it's an important one to remember. This next one is a little bit different. This next F value up here. So going up to our clearance ratio, our renal ratio. Essentially, this is our clearance renal before, right? This is what we calculated down here. So this is like a rate, this would normally be in milliliters per minute. This could be really a number of things, just depending on how much a drug gets metabolized. It could also be milligrams per minute if it's in terms of a drug. That's where some of these things get a little bit weird, is the units. And I'll show you how we can kind of distinguish those a little bit more when we do a math problem. But essentially, we have our renal clearance, right? And then we have this FU. Now, this is the fraction of a drug unbound. If I can spell. Unbound. And you might also see this as FUB. This is not urinary, and that's really important. I thought it was when I was first looking at this because it was used almost exclusively in the urinary lectures at first, but it does come back a little bit in the hepatic lectures, which I will cover as well, how you use that one. Essentially, this means when a drug is bound to a protein, it's inactive, right? Or we can't filter it, it doesn't have any action, it's just kind of stuck in the blood. So our fraction unbound are just drug particles that aren't bound to like big proteins. This is a protein. Let's say these blue things are drugs. So these are bound, right? We have 3 drug molecules, and then let's say we have 1 free floating that's not bound to our protein. Our fraction unbound would be 0.25 or 25%, depending on how you want to write that, right? So this is really important because this is a drug that can actually be metabolized. It can be excreted. And this can vary, right? There are some drugs that don't like binding to proteins. But this one, for example, this has a relatively low fraction bound. This is pretty highly protein bound, so it's not going to get excreted as readily. And then the final thing in our equation is GFR. Not too hard, right? We just described it, either 120 or 125 milliliters per minute. And essentially, this will get you the ratio that something is excreted renally. This can be really useful for essentially finding out not how much drug is sort of, because before when we talk about an equation like this down here, right, we could find the fraction of the drug excreted renally by doing this over this. This is now a subset of CLCR, or CLR. This is essentially for each time a drug passes through the kidney, whether it's bound or unbound, how much is actually taken out. So let's say this is the out pathway. So this is our ratio, right? Let's say we have 3 drugs. These 2 go through. This one gets sent out. Our CLR ratio, our cleared by the renal for the each time would be 0.33. Because this is essentially each time a drug molecule that is unbound will pass through the kidneys, how much actually gets out. And this varies, obviously, because the kidney has multiple processes, which we'll talk about down here. There is filtration, there is reabsorption, and there is secretion. So let's think about each one of these logically. If you remember kind of the structure of a kidney, we have the glomerule, just kind of like a tube, and then it goes down into our nephron, and then it goes out in the distal tubule, right? So filtration, if you remember, we got a ton of like blood vessels curled up in here. It's when our drug just goes in traditionally, right? It diffuses through the glomerulus into the Bowman's capsule and goes down through the tubules. So essentially, if our ratio is 1 right here, right, what we find up here, this means the drug will pass through normally. There will be no way it gets in, there will be no way it gets out. It just follows its path, it behaves, and we don't need to worry about anything. This is probably the most basic pathway. This is true for bigger drugs. Now, if you remember what reabsorption is, this will usually happen in the distal tubule. This is kind of what we were talking about before, where 1 will escape, in our example where our ratio was 0.33. This essentially means that drugs will get reabsorbed into the bloodstream. Let's say this is another blood vessel just out in the body that's not part of the kidney. If a drug moves through here, it'll go back into the blood, and it won't be excreted, right? And if we're measuring the drug particles that are actually in the urine when they come out of the body, we'll notice a shortage, right? Because that drug is still in the blood. So essentially, this 1 is what we expect if a drug behaves well. If we have less than what we expect, which remember is 1, aka gets reabsorbed in the body, that means there is resorption, which makes sense, right? If a drug is resorbed, we get less than we think we're going to get in the urine. Now for our final case. So remember that filtration was what we expect. Reabsorption is less than we expect. So that means secretion is more than we expect. So up here is our blood vessel. And essentially the opposite is happening this time. This blood vessel may pass really close to this nephron, and some drug that's in the blood actually might have an affinity to go in here for one reason or another. This could be due to pH, this can be due to other factors, different types of transporters, but essentially, let's say we're expecting a certain amount of drug in the urine. Remember, what we expect is always 1, but then we get more. This is secretion because all this drug is being secreted from these blood vessels back into the nephron. So all of a sudden we get way more drug out here than we expected initially. So that's kind of how you can think about these logically if you ever need to work one of these out. I bet we will get a question on this. So I just wanted to kind of make that more clear with a picture. So I hope that was able to clarify sort of what we mean when we use these terms. Next up is acid-base kinetics. We didn't really cover these in class. I don't really think he's going to ask them, but they were on the equation sheet. I will go over them briefly. These are essentially just concentrations. Concentrations in urine, concentration in plasma, right? We'll be given both of these. And then it's just plug and chug. Because essentially we can always isolate one of these. If we have the pH of plasma, which you know is roughly 7.4, right? Between that value of 7.35, 7.45, and then maybe he'll probably give us pKa because it's honestly pretty hard to isolate that. So it'd probably be like we solve for something like pH of urine. We don't know what that is. And let's say the pKa is 7. Let's say the concentration in urine is, I don't know, like 5. This is like 10. This is just things we can isolate, right? It's just kind of plug and chug. And setting up this equation algebraically. I don't have a practice one of these for this because I don't know what a realistic example would look like. Like I said, just plug in numbers. He will give us everything. So just knowing essentially what these mean, right? Urine, plasma, pH urine, pH plasma, pKa, right? 5 different things. He'll give us 4 of them. And then this is the equation for acids. This one down here, equation for bases, very similar. The only thing to note is that they're essentially flipped. So whereas pK is being subtracted before, it is actually the thing being subtracted from. And then it's still pH urine in the numerator and pH plasma in denominator. So just know if you're subtracting pH from pKa or pKa from pH. Just look out for that because they are not the exact same equation. I wouldn't want anyone to get tricked. Next up, this is probably the most complicated concept that could be on this exam. This is essentially rate of renal elimination over time, which obviously isn't going to be linear, right? Because as we get more drug being eliminated from the body, whether that be hepatically, whether that be renally, even like through biliary or sweating, whatever, this is going to go down over time, right? The rate this is eliminated. So what do we have here? du dt, nobody likes calculus, so honestly, just think of it as the change in the drug in the urine over the change in time. That is all this is saying. And what these little d's mean is just at a certain moment in time. So for example, at exactly 2 hours, what is this rate? That's something we can model with this, but don't worry about that. Just think of it as change in drug over change in time. This equals to the Ke, which if you remember from all the way over here, is our renal elimination constant. The drug in the body at time 0, this is equivalent to your dose. Something really handy about this one is in the past, this has been our dose divided by our volume of distribution, right? So like our dose 0 over BD, this is not. This is literally just dose. So you don't even need to worry about volume of distribution when solving a problem like this. Just focus on the dose. And then e to the negative k10t, something we've seen a million times. Notice this one is ke, this one is k10, meaning this is our total systemic elimination, and this one is only our renal elimination. Next up are just some alternate forms of this equation. If you take the natural log, something we can actually get is a linearized equation, right? Since ke and db0 are constants, the natural log of them will also be a constant, and then k10 a constant times time. This will be a linear equation. So this will look something like this. I don't know if they start off at exactly the same slope. I don't really care. I'm never going to linearize this equation. Neither are you. We don't have graphing on the exam, but that's how it would look if we did it. And then these equations are the same. This is kind of what I talked about up here. Change in time over change in, or change in drug over change in time. Means the same thing. Don't worry too much about it. And last thing I want to talk about on this page is the fraction eliminated in urine. This is really, really useful. And it's something we also talk about over here. Your fraction eliminated in urine is your only way to, well, not your only way, but your only way non-graphically to find your drug eliminated in urine at infinity. And this equation makes sense, right? You can look at this as Ke over K10, which is a totally valid way to solve for this. But if you don't know starting dose, so like starting dose unknown, this can be a really good way to extrapolate this, or you can reverse engineer this. Bioavailability, right, is F times dose divided by this. So this makes a lot of sense when you think about it. Let's say we give 1,000 milligrams of a drug, and we know that 900 milligrams is excreted in urine. This means our fraction eliminated in urine is 0.9, which makes sense. And if we knew this 0.9 initially, it'd be just as easy to reverse engineer this equation. So what's 1,000 times 0.9? If we were to move this over here, it's 900 milligrams. So that can give us our du infinity, our drug eliminated in urine at time infinity. So really useful. Again, just knowing this is the only way to get this, because this is something that comes up in problems. I'll be working out how to show this here in a second, but that's a very important equation to know. Okay, so now I want to teach you how to actually do kind of a graphical problem. Now, obviously on the exam, we won't be able to graph, but assuming we're given a graph and needing to extrapolate some values for it, I want to show you what you need to look out for. And there's actually two ways to do this. The first way I'm going to show you is the way you should always use. I'm going to briefly go over how to do the second way, but to even do the second method, I think you need values that you calculate from the first method. And also the rounding is just completely wrong in this problem. In this problem, for reference, it is a problem Dr. Desai gave us. It's the extra practice problem that did not have an answer key. So here's your answer key for that if you were wanting that, just to check your own work. But yeah, let's get into this. So I'm trying to color code this the best I can. If you were wondering why there's 3 different colors in our little table here. The purple is something that every one of these methods will use. We have the time intervals, the drug concentration, and the urine volume. These are what you will always need for every method. So if you don't have one of these, it's impossible to do a problem like this. This orangish red are for the first method. These are values that we really only need for this. This column right here, you could argue, could be used in both because you kind of need it. And I'll go back into that briefly a little bit later, again, why the method in blue it doesn't really make sense, but let's just see what we're given here. So between the time intervals of 0 and 2 hours, that top row there, a patient produced 200 milliliters of urine with a drug concentration of 0.006. I believe this is milligrams per milliliter? Maybe it's milligrams per liter. It doesn't really matter. I mean, it kind of does, actually. Yeah, okay, it's milligrams per milliliter, because we eventually have to multiply these together, and that'll be something we talk about. But, anyways, and essentially we are trying to find out the fraction excreted in urine. We're also given this equation, which we will not really use yet. We will use it in a little bit. This is our accurate equation, but we're gonna try and extrapolate a urinary equation. How do we do that? You can see I generated a chart down here. This would probably be a chart we're given. These axes didn't really get labeled. So what we have on the bottom row here is time. On the independent axis, this is time in hours. And then the y-axis is a little bit different. This is kind of our change in drug over time. So that's essentially, it's what's graphed here, I believe. Let me double check. Yep. So this is the change in drug for our urine for each time interval. So for example, between our 0 and 2 hours here, over the course of 2 hours, there were 13 milligrams in drug in the amount of urine that were produced. So essentially what we're doing is, since this is a 0 to 2 hour time interval, we're taking this 13.2, right, this is our change in drug, divided by 2 hours. this is our change in time, and that'll get us 6.6. But we don't plot this at 0 hours, and we don't plot this at 2 hours. We actually have a value called T mid, which is right here. And this is the midpoint of our time interval. So for this first time interval, the middle of 0 and 2 is 1. Where it gets a little complicated is we're finding the midpoint between 2 and 5 next. So instead of that being 2.5, it's not the difference between 5 and 0, it's 2 and 5. We get 3.5, and that's where these are graphically. So this first hour mark is at 1, this one's at 3.5, this one's at 6.5, etc. And those are all of these values. So for example, I'll do one more. We have our 17.05, which is our 0.062 times this, our urine, gets output to this is our total number of drugs divided over 2 minus 5. So we have 17.05 for 5 minus 2, which is 3. And with that, we get 5.68. So essentially what we're doing is we're graphing a rate here, right? This is this amount of urine. So this is like milligrams of urine per hour that's excreted, and that's the slope at this point, at this point, at this point, etc. Right? Doesn't really matter. What matters is the equation we generate from it. So I'm going to erase this really quick. Feel free to pause that and go back, just so I have a little more space to work with. And so as you can see, we have a mono-exponential equation, which we have this value 7.207 e to the negative 0.061. So this is the first thing we need from our equation, which we technically didn't need because it was already provided. This value right here is our K10 value, right? Our total elimination constant. You can see that's really close to the estimated equations, 0.06. They're practically equivalent. So that means we're on the right track. And as I will show you with the next method, they are not equivalent, not even close. So please use this method. This other value, though, this isn't so much of a plasma concentration as it is, I'm not even quite sure how to describe it. I think it's technically an instantaneous rate excreted in the urine, but that's not a plasma concentration. That's not helpful. Something like this 2, this is a plasma concentration, but this 2 is for the whole body. This isn't for the urine. So how can we get from one of these to the other? Well, this value right here, which is, it's essentially equal to Ke times our initial dose. And if you remember, Ke is our, I'm sorry, not our dose. So, okay, no, I had this backwards. So, this is just some arbitrary concentration, but this is equal to our dose, our starting dose. I have that backwards again. Sorry about that. I was right the first time. So it's Ke times dose. Ke being the renal elimination rate constant, and then this 7.2 being equivalent to some concentration, right? Or some rate of elimination. So what we can do is we can substitute. We can put 7.2007, and then this is something I forgot to give you. This problem initially had 200 milligrams IV was given. This is also helpful because since we know it's IV, we know there's 100% bioavailability. So we have Ke equals dose, which is 200 milligrams, times, or not times, I'm sorry, that's just milligrams as well. So essentially we isolate for Ke. So Ke equals 7.2 over 200. And with that, we get our Ke value, our elimination constant for urine, to be 0.036. Now this is good. Another thing that we want to keep in mind is the Ke can never be bigger than K10, right? Because K10 is everything. It wouldn't make sense if it was bigger. In this case, it's about half. Let me do the math really quick to find out exactly what fraction is excreted in urine. And if you remember back from one of our previous equations, Ke over K10 equals Fe, or the fraction excreted in urine. So let me really quickly do 0.036 over 0.061. So this is about 0.59 or 59%. So this drug is primarily excreted in urine. It has some other pathways, but knowing this, I'm going to put our 0.036 over here, and I'll start at 0.59. And then I'm going to erase this. So this is good. That's pretty much all we needed this chart for. We just wanted that KE value. And remember, the way we get that KE is by looking at this number. This number is critical, so that's why we generated that graph. Pretty much the only reason why, in fact. Because everything else we actually do with our original equation, which should look a lot more familiar. So first up, we have our equation that essentially just says, assuming we start with 200 milligrams, this is the concentration of plasma. This is 2 milligrams per milliliter. And then we don't know our volume of distribution. So this is essentially just our dose times concentration times VD, right? This is an equation we've seen since the first exam. So if we isolate VD, we divide this side by 2 milligrams, we get that the volume of distribution in this problem is 100 milliliters. Or I'm sorry, 100 liters. Because this should have been liters. I'm sorry about that. Yeah, so that's liters. So that's how we get 100 liters here. And these units are important, right? And this is just something you can do kind of with common sense. If you get a number like 200 milliliters for a volume of distribution, that's so low. You know, it's probably liters, and it's probably like what I just did. I just made a mistake in my units somewhere. So again, just important to keep an eye on, because units do become a little important here in a second. For the one time in this class, they actually do. I promise. So now we actually want to find our total clearance. So we can do that. So our total clearance, I can't draw the letter T, or this could be clearance S. Remember, just total or systemic is equal to our volume of distribution times our K10. Now we could use either one of these K10s here. We could use this 0.061 or this 0.06. I'm going to use the 0.06. It's a little more accurate because remember, this other equation is from the graph we generated, which obviously has a little bit of error. You can see right here, it kind of loops away from the trend line. So it's not a perfect model. But essentially we'll do 100 times 0.06. And we get our total clearance to be 6 liters per, that looks like a 2, kept trying to fix it. 6 liters per hour, and it is hour, right? Yep, because the K10 is in hours. So again, that's just me double checking my units, just to make sure. And then we actually probably want this in liters per minute to be totally fair. I'll show you why here in a second. Or milliliters per minute would work fine. Yeah, we'll switch this to milliliters per minute first. So, actually, no, there's one more thing I want to show off. So we'll keep this as 6 liters per hour right now. If you remember, our clearance renal is equivalent to VD times KE. So we can do something really similar here. We can do our 100 liters times our 0.036. And this is equivalent to 3.6 liters per hour. So that's another really nice thing to have. Let's assume for a second that our drug is only excreted renally and hepatically. So that would mean our clearance total is equal to our clearance renal plus clearance hepatic. And we'll do a little more with hepatic here in a bit. I'll just generate this number on this page. We have 6 equals 3.6 plus clearance hepatic. Isolate that, we get 2.4 liters per hour equals clearance hepatic. So I'm going to write all these off to the side, and then I'm going to erase some things. So clearance hepatic equals 2.4. Clearance renal equals 3.6. Clearance systemic equals 6. These are all liters per hour. Okay. So essentially, the reason we did all that work before is, remember, just for our Ke constant. That's why we had that graph. But that volume of distribution was something we could have gotten from the beginning, right? We already had the 200 milligram dose. We already had the plasma concentration from those pre-provided equations. So really, this is kind of getting up into the weeds. It's very specific, very niche what we're doing with these for very little payoff. Because as you can see, I generated an entire table, an entire line graph just to get a single value. So the last thing I wanted to show is the clearance ratio, which is equal to the clearance renal divided by the fraction unbound, because remember that's what FU or FUB stands for. And remember, so if it's 0.3 unbound, that means that 70% is bound. So this is a pretty high plasma protein bound drug. And then this is over our tubulin, I believe the protein is. But it's just GFR. That's all it is. I'm going to be using 125 milliliters per minute. So this is important here. Since our units right now are actually in liters per hour for our renal, we do need to convert this. So we have 3.6 liters per hour times 1 hour, 60 minutes. And then this is in milliliters per minute. So we can do 1,000 milliliters in a liter. So let me see what this equals really quick. 6 divided by 60 times 1,000. Okay, we get 60. 60 milliliters per minute is our renal excretion, or renal clearance, sorry. So if we have 60 milliliters divided by 0.3, right, from this value right here, divided by 25 milliliters per minute. We're at 125. We get a value of 1.6 as our ratio. And remember, essentially like 1 is our normal value. This is what we would expect if we wanted this to be a perfect world. So what happens again when we get above 1? Well, this means that there's secretion, right? This means blood vessels are actively pumping out whatever drug substance this is from, let's say this is our nephron right here. Then we have a vein running by it. This vein is dumping things back into our proximal tubule. And that's essentially what makes this go above 1. So that's something we talked a little bit about before. But yeah, I think that's pretty much everything for renal calculations. I didn't go over the pH, but again, I think that's just plug and chug. There were no practice problems on it, so I'm not too worried about it. But just remember, the biggest takeaway from this slide, I'm going to circle it in purple, it's my favorite color, is that this 7.2 is equal to your dose. I meant to write dose, not 200. Dose times Ke. And you're looking for Ke. That's the whole reason you do this big, annoying graph and table. This is like the most valuable thing. So don't forget that. Your Ke is like your bread and butter for this unit. Now for the fun part, we get to talk about the stupid method. I won't take too long on this because I don't want any of you doing this unless you really, really like this method and for some reason understand it way better than I can possibly seem to after trying to figure it out for 2 hours or so. So if you understand this method, and if I mess something up, leave it in the comments. I'm pretty sure I did this right. It's just dumb. There's so many rounding errors. Essentially what you're looking at is this is the value before that I mentioned could be used for both. And here's why it's used for both. What you're looking at here is your drug total, and that's eliminated in your urine, right? So essentially, it's the summation of these values. So 13.17.05, it's this. And these just keep summing. These make their corresponding values. Okay, fair enough. I get that. But then what you need to do is, back on the previous slide, we established that we had a 200 milligram dose total, right? All well and good. Except for this, you don't. This is a subtraction, right? This is your drug excreted in the urine at time infinity, which is essentially all your drug excreted in the urine. Okay, fair enough. and then you just subtract it for each one of these values. But the problem is there's a key component here, and this isn't total drug. This is drug excreted in the urine, meaning to be able to solve this problem, we would need to know the amount of drug excreted in the urine. And where do we get that from? Oh yeah, from doing this. So we can't even really generate this graph because this right here is our y-axis. And this right here is our x-axis. These are just the time points. This doesn't use the t-mid. This will use the time points like 2 hours, so like the ending interval. So 2, 5, 8, right? You get the picture. And graph it that way. This was obviously Ke times dose. Okay, this is the same problem. So dose is 200 milligrams. So what's so times Ke? Sorry, I'll write this all out just for fairness sake. 61.25. Okay, cool. So we need to divide 61.25 by 200. We get a Ke of 0.3, not 0.03, 0.3. Because remember, our Ke value was 0.036. Okay, bit of a rounding error. Quite a bit of a rounding error. Whole order of magnitude. This right here, K10, right? K10 is actually 0.06. And you might be thinking, well, Ryan, maybe you have this backwards. Maybe this right here is the Ke, and that's how this problem is solved. It's not. I took these from Dr. Desai's lecture slide for a different problem. K10 is 0.88. That's this right here. This is the way to do this method. This method might work better on a different practice problem, but for this, there were just so many rounding errors. I mean, you can see how terrible this line of best fit is. Yeah, so this method is stupid. You use the first method I showed you because, you don't need the answer to be able to solve the problem with the other method. So, yeah. Okay, one last slide. Luckily, this one's a little bit easier. We'll be building more on the problem I was talking about before, but not by a whole lot. I just want you to think about the liver really quick. So the liver looks like this, right? We have a vein that goes in it, or an artery that goes in it, I'm sorry, and a vein that goes out of it. Let's say we have 30 milligrams of drug go in, and we have 27 milligrams of drug come out each time blood passes through. This is what we call an excretion fraction, and essentially it's the absolute value of initial minus final over initial, right? So, and that's what this term right here is. This is excretion fraction. So in this case, our excretion fraction would be 3 over 30. It's 0.1. So pretty low. That's all this concept is, right? It's how much goes in and how much comes out. But then we have this Q. This Q is actually really nice. It is more or less a constant. It is the blood flow through the liver. Right, so this is kind of the rate that things are passing through. So we have 1.5 liters per minute. This you can assume to be constant. Think of this as like your GFR, which is 125 milliliters per minute. This is 1.5 liters per minute. So you can see actually that the liver is quite blood supplied, all things considered, which makes a lot of sense, right? The blood kind of comes back through the, well, I mean, there's the portal arteries and veins. I'm not an anatomy expert, but you get the picture. A lot of blood passes through the liver before it goes through the vena cava. So it makes sense that this is higher than the kidneys. But anyways, yeah. We have our QH, we have our excretion fraction. E is equal to EF. You will see it written both ways. Do not freak out. Same thing that we just solved for right here, which is essentially just what percent gets taken off each time something passes through the liver. In this case, it's 10% in that example I gave. But how do we calculate this from a real world problem? Well, if you remember, we did have our hepatic clearance for the previous problem. I believe it was, did we say 2.4? I think we said 2.4. If it was 2.5, I'm sorry. Liters per hour is equal to our liver clearance, or our hepatic clearance. So what we can do is, since this is in liters per minute, we will need to convert this hepatic clearance into liters per minute as well. So we have 2.4 liters per hour times 1 hour 60 minutes. When we do that, we get 0.04 liters per minute. So now we can simply do 0.04 divided by 1.5 liters per minute, right? I can write that out. So we have our clearance hepatic over our QH. That's where this comes from. And this is also equal to EF. So 0.04 divided by 60, get a really, really small number. 0.0006. So very small excretion fraction, which is true in most cases, right? Especially for a drug like this that's more renally excreted. That means that for each time this passes through the liver, 0.06% of it will be eliminated. So let's say we have 10,000 milligrams of a drug passing through each minute. If we multiply this by 0.06, or yeah, 0.06%, so 0.0006, we get that 6 milligrams is removed each time it passes through. So now let's take a look at this crazy table. Oh, and here's an equation too, by the way. This equation doesn't matter too much. It is there. CL int stands for clearance intrinsic. I tried looking up what that was. It always came up as the intrinsic clearance of the liver. However, I don't know how that's different than clearance hepatic. I don't think we will be asked this. This is not on the equation sheet. This was in the slides, so I thought I'd include it here. But it kind of ties into this. A low E value will essentially mean that there's two schools of thought on this, what limits the rates of these. For a low E, it's enzymatic limitation. And this kind of makes sense, right? There is way more drug passing through, and only a little bit of it is getting destroyed. So it's the enzymes that are limiting it. This might not be a CYP substrate. It might be something else. It might be something that's hard to metabolize. So for a low E value, enzymes are rate limiting. And then apparently they can be modeled by this equation. That's not incredibly important, but it is there. For high E, it is blood flow limitation, which kind of makes sense, right? It's the opposite. So essentially, let's say if our E value instead was like 0.9, every time this 10,000 would go through, we'd be losing 9,000 milligrams of drug for the first time. Obviously, the second time we go through, there'd only be 1,000 left. So then it'd go down to 10. You get the picture. It seems like the enzymes are able to pretty much completely take up this drug. Really, the slow part is this blood flow. So the clearance here you can see is directly proportional, more or less, to blood flow. Whereas here, it's more proportional to free drug and then also intrinsic clearance as well as blood flow. This will probably be a question in some way, shape, or form. That's why I highlighted this. But the math itself does not matter. Last thing I think we might get a question on is this table. We can try it for our equation we calculated. So this right here, like we mentioned, is EF. And that's kind of the vertical axis of this, right? You can see it goes up by increments of 0.1. So since we are 0.0006, we'd be way down here. And if you remember from before, our fraction unbound was 0.3. So we're pretty much at the 0 mark right here, right? But that's just on our vertical axis. We also need to consider our horizontal axis. So essentially, our fraction unbound, we go 1, 2, 3, 30% unbound. So what kind of capacity is this limited in? This is limited in binding, and it's insensitive. So essentially what this means is I believe this is sensitivity to enzymatic activity? I forget exactly how this was explained, but essentially its capacity limit, yeah, I think this has to do with enzymes. So for example, if something is drug bound to plasma protein. No, okay, I'm doing this backwards, sorry. So this is bound to plasma protein. So I was still right for the vertical axis. I'm glad I caught that. So we'd actually be at 0.7 here. So this is essentially sensitive to changes in enzymatic activity, right? Bound to plasma protein. Sorry. I clearly didn't know this as well as I thought I did. It's okay, we're both learning right now. I think this is just this seems backwards because like I guess what I was thinking is if it'd be insensitive if it was highly bound to a protein because it wouldn't require more enzyme. But I guess it's backwards. So just remember it backwards. If it's really bound to protein, it is sensitive. If it is not very bound to protein, it's insensitive. We're probably never going to see this again after this exam, so I think I'm going to leave it there. But thank you so much for watching and learning with me. Like I mentioned before, I don't know if I'm going to do a video for the PK final just because I think it's going to stop being math, and I know people usually watch more for the math than they do for the reviews, which is whatever. But yeah, thanks for watching PK, and good luck.